So in this class, we will discuss an important concept called redistribution of moments, which is normally applied in the design of fixed beams or continuous beams or any indeterminate type of structures. So here I consider the examples of continuous beam. In the first example, I will take all the three supports as simple supports. In the second one, I will take end supports as fixed supports and the intermediate as simple support. So by the behavior of continuous being subjected to UDLs, the general case of loading, so you can observe that at the midspans, sagging bending moments will develop, and at the supports, hogging bending moment will be developed. So that you have learned in your structural analysis class. Now here I have shown here so the nature of bending moments here. In this case, at the midspan, sagging bending moment will develop, and at the support, intermediate support, hogging bending moment will develop. And here also at midspan, sagging will develop. So that means MB and ME they are sagging, whereas MB is hogging. Of course, ME and MC will be zero because they are simple supports. In the case of fixed beam, the fixed supports at the ends, MD and ME as usual they are positive, that is sagging, whereas MA, MB and MC they are all hogging, negative. So the nature of reinforcement at the supports and at midspans will be different, because when the moment is sagging, then we are going to provide the reinforcement like this. That is at the midspans, we are going to provide the main steel at the bottom, a compression steel at the top. Whereas at the supports, it is reversed. For example, at section B, the main steel will be provided at the top, compression steel will be provided at the bottom. So that are all those designs you are learned in your RCC. So here, in the case of continuous beam, two types of reinforcements we are going to provide. So at the supports means here, at B as well as at C and at A. So you will be providing reinforcements like this. Main reinforcement at the top and compression for the bottom, or nominal reinforcement at the bottom. Whereas at the midspans, that is at the D and E, it will be like this. Main reinforcement will be at the bottom, compression reinforcement at the top. Now, how to consider this redistribution of moments? That is a very important criteria. So let us take a fixed beam like this. So a fixed beam, in case of fixed beam subjected to UDL WU, so that is the design UDL you can take. So the bending moment diagram will be like this. So you will be having hogging bending moment at the supports, which is equal to WU L square by 12, and sagging bending moment at the midspan D, which is WL square by 24. That means you can observe here that the sagging bending moment at the midspan is half of the hogging bending moment at the supports. That means the moment is not uniform throughout. So irrespective of nature, or whether it is positive or negative, so the bending moment value differs from section to section, and at these two points are the points of contour structure, so where bending moment is zero. That means if you cannot provide different sections at different points according to the moment. So that is why Code Provision IS 456/2000 it gives one idea about the redistribution of moment from the supports towards the center. Because if the support moment is high towards center, that moment can be redistributed. That is the meaning. So that is done based on the concept of plastic collapse. So which you have studied in your steel design. So this is whatever bending moment diagram here we have written. This is the elastic bending moment diagram. That means the material is still in elastic state. It has not gone to plastic state. Now what happens? The plastic state means at typical sections or critical sections where the maximum bending moment occurs or maximum shear force occurs, maybe positive bending moment or negative bending moment, hinges will form. Plastic hinges will form, which cause rotation of the member, and finally it leads to failure. The failure itself is called as collapse. So formation of plastic hinges, sufficient number of plastic hinges in this structure will cause the collapse of the structure. So that means the entire structure will be having one value of MP. That MP value is called as the plastic moment capacity of the section. So once that MP value is reached, so we say that it has attained the plastic state, and this MP value is uniform throughout. That means to achieve that MP value, what happens? What we can do is we can redistribute the higher moment towards the lower moment. That means from the support towards the center of the mid span, we can always redistribute the moment. That is what I have written here. So moment is redistributed from the supports towards the center. Collapse takes place after the formation of plastic hinges at supports and also at some points in the span. But this redistribution, there are two important conditions for applying this redistribution concept. The first condition is a maximum of 30% redistribution is allowed. That is, maximum moment can be reduced at any section up to 30% only. So that is one condition. That means you can redistribute the moment up to 30% to a section of lower bending moment value. And second condition is whatever may be the percentage of that is from 0 to 30%. So the equilibrium between internal forces and external load should be satisfied. So this is the basic equilibrium equation that should be satisfied even after redistribution of the moment. That is those two conditions should be satisfied as per the IS. Now to understand the concept of redistribution, I have taken an example here. Suppose you are analyzing a continuous beam where you got the moment at the support as 400 kN. Actually this is negative. And moment at mid span you got 200 kN, which is positive. So sagging and hogging. Now suppose if you allow for 20% redistribution of the moment from the supports towards the center, so the design moment we have to take at the support as, now we have to reduce this by 20%. So it becomes 400 minus 20% of 400, that is 0.2 times 400, which becomes 320. Now we have to take this 320 kN as the design moment at the support, and at the mid span, moment is increased because we are reducing this moment at the support and we are increasing the moment by the same amount at the mid span. Now the design moment at the mid span will be, so obtained moment is 200 plus 20% of this 400 which we have reduced. So that means it is 200 plus 80, 280. That means we have to design the support section for a moment of 320 instead of 400, and we have to design the mid span section for a moment of 280 instead of 200. So that's what we are going to do. So you can see here the difference between these two values is very much reduced. Here the difference is 400 minus 200, that is almost 200 kN, whereas here the difference becomes 320 minus 280, that is 40. That means since the difference in the moment values it is small, so almost we can provide uniform section throughout the span of the continuous beam. That is the idea. So otherwise, if you take 400 and 200, if you design the section, so you are going to get different sections for 400 and 200. Almost the depth will be double for 400 compared to 200. So you need not provide the same section throughout. It becomes uneconomical. Therefore, we use the concept of the plastic collapse, which takes into account the material strength till the yield point. That is the advantage. Now, suppose if you take 10% redistribution, then what happens for the same history, design moment, empty means design moment at the support will be 400 minus 10% of 400, that is 40, so 360, it becomes 360. And at the mid span, it is increased by 400, 200 plus 40, 240. So here also, the difference between these two is 80 kN/meter. So you can see that as the difference reduces, here 400 minus 200, here 360 minus 240, as the difference reduces, you can have uniform section throughout because almost it will carry uniform bending moment. So this is the advantage. So design of reinforcement is done for these values of design moments by using SP16 IS 456, and reinforcement pattern differs as I already told at the supports as well as at the mid span. That means in the case of a two-span beam. So you can adopt this redistribution of moments concept. Whereas in case of free span continuous beam, I have used coefficients. So that example I have explained in the other video lecture. You can go through that. So which is coefficients, bending moment coefficients and shear force coefficients. They are available in the IS 456 tables 12 and 13. That I have used for designing of 3-span continuous beam. For 2-span continuous beam, let us use this redistribution of moments concept. So in the next lecture, video lecture, I will be taking the design of a 2-span continuous beam using the concept of redistribution of moments.